Okay, good morning, everyone. Today it is for me a really great pleasure to present to all of you today's speakers. Today's speakers is Dr. Bénédicte Cuenot from Fax. Dr. Cuenot graduated from École Centrale Paris in 1990, and then she defended her PhD in 1995 and her HDR in 20s, both defending a thesis in numerical combustion. Bénédicte, she is now the leader of the combustion group at Fax Research Center in Toulouse, south of France, developing advanced and massively parallel software for numerical simulations, both DNS and LES, of turbulent reactive flows called plasma and heat transfer, including radiation in industrial systems. Her research covers a very wide topics of combustion, from pollutant emissions, ignition, extinction, combustion efficiency, and thermal fatigue. She has a very impressive publication record. Indeed, she published more than 100 peer-reviewed journals. And since 2018, she has been distinguished as a fellow of the Combustion Institute, and she is in the editorial board of the journal Combustion in Flame. Furthermore, Bénédicte, she will be co-chair of the next International Symposium on Combustion that will happen in 2022 in Vancouver. Today, she will talk about a prediction of pollutants and soot in turbulent flames. Bénédicte, the floor is yours.
Thank you, Davide. Thank you very much for the introduction. And it's my real pleasure today to show you some of our works we're doing on prediction of pollutants, including soots. This is a joint work, of course, of the whole CFD team at Surfax. You have all names here, including Davide, who just introduced me here. And so you will see some names from time to time on the slides. So, of course, the motivation is quite clear. We all know that combustion leads to emissions. I just wanted here to illustrate the variety of sectors that are concerned. It can be transport, either air transport, but also maritime, and of course ground transport with cars and trucks. But we also know that combustion is very important in industry, furnaces, also for domestic use. And there is also an environment component, including fires. So this is a major concern now, and it motivates a lot of works to better understand and control these emissions. We all know also the various environmental impacts. This is a point that I wanted to make today. It's probably clear for everybody, but just to make clear that, in fact, we have two types of emissions. There is one type that is more related to urban air quality, like nitric oxides, carbon monoxide, and so on. And we also have another important consequence on global warming and climate change. And these are different topics. They include different molecules, like for climate change, it is CO2, but also H2O in some extent. And of course, soot is important for both aspects. It's a problem for urban air quality, but also for global warming through what is so-called condensation trays, which I illustrated here at the bottom of the slides, with where you can see condensation trays from aviation here in the clear sky in the left picture, but something that is maybe not so well known, that boats also, maritime transport also generates condensation trays. As you can see here, I think it's the Pacific North Sea, you can see these traces that are typical of condensation trays. And these condensation trays may increase the sky covering and enforce radiation in the global Earth climate picture. So yeah, depending on what target, what type of problems we want to work, we may have different solutions. Of course, everybody works toward low NOx and low carbon, as we've seen. So low NOx for, again, urban air quality, low carbon maybe more for climate change. And there are a lot of different ways, technical ways to decrease combustion emissions, among which I tried to categorize of global classification. First way is to work on mixing and how air and fuel mixed together. It can be through staged combustion, as done, for example, for aviation engines, but it can be also through swirl or other types of injection strategies. Another important way to decrease the emissions is to work on the fuel nature. So, of course, H2, in France at least, we hear a lot of H2 right now because it's no carbon. So it's very attractive. We also know that it raises other issues, so it's not so easy to do, but it's considered. Ammonia is also very much discussed right now. And in a more conservative way, we also have a bunch of alternative fuels where that have different compositions that may lead to decreased carbon emissions. A third way is to work on the efficiency, combustion efficiency. Like in car engines, there has been a lot of progress made with downsizing, which really makes a lot of progress in the efficiency of these systems. In helicopter engines, we recently seen the spinning combustion concept that has been developed by Safran helicopter engine, where they also this also allows to increase the efficiency quite a lot. So this is a very interesting way. And finally, we also try to work on the combustion regimes to go lean or ultra lean, possibly with as other devices like combining with plasma-assisted combustion, for example, to be able to ignite and sustain lean or ultra lean combustion. Oxy combustion is very popular right now in the industry, using furnaces like in steam cracking or glass or whatever, this kind of applications, where they also include possible CO2 dilution to again decrease more the emissions. So all these different techniques include different physical phenomena that are in play in the combustion system that I try to synthesize here in this slide. So, of course, we concerning mixing, the way you mix air and fuel, this is linked to the turbulent flow that usually is in these systems, the flame structure, and the possible multiple combustion regimes that it can lead to. A major aspect, of course, is chemistry. We all know that just to predict like a film length, you don't need so much detailed chemistry to have a correct heat release rate, and so the correct flame length and shape. But if it comes to predict pollutant emissions, this is another story, and you really need to go further in the chemistry description, and this is a major challenge. And we also have to take into account other complexities, like the fact that fuel in most systems is in a liquid state, leading to spray flames, and so related physics like atomization and spray combustion, two-phase combustion. So I will try to give an overview of what we do on that at Surfax on all these physics and related modeling. But one important aspect is that in our team, what we try to do is really to obtain predictive trends. Like, we want to be predictive. We want to give useful answers to engineers. Useful answers mean either an accurate prediction or an accurate trend. This requires to apply our models and simulations to very simple flame configurations, laminar flames, to down to the most complex system, the true industrial system with all its complex geometrical complexity. So it is very important for us to really validate as much as possible in this left part of the slide on these configurations that are more or less simplified, with an intermediate here that is a lab scale set of configurations where you still have good access to measurements and for validation, but are where you are quite representative of the true exact industrial system, and then we apply to the industrial system. So this is what I will try to show in this lecture, how we can validate, develop and validate our models, and to have confidence to give good, correct solution in the true industrial systems. I will not show so many true industrial applications because of confidentiality issues, as you may understand, but I will show a lot of illustration on the first two categories. All what I will show today in terms of simulations and results have been obtained with our in-house code developed at Fairfax, which is called AVBP, which has the necessary features to handle all these applications that I have just mentioned. So it is able to compute either external or internal flows. It is fully compressible because compressibility is a key feature for combustion instabilities and thermoacoustics. And it can work in both DNS and LAS approach. I will come back to that in a minute. It handles complex geometries, so for that it uses unstructured meshes. It is highly parallelized with good efficiency. It is explicit in time with center schemes to reach high sufficient order, what we call high order. For LES is second, third order. And it includes a lot of models and numerical techniques. They are not all listed here, but I will give you an overview in this lecture today. It has been applied to many different applications, all linked to combustion, of course, gas turbines, piston engines, rocket engines, furnaces, and so on. So the first point we have to deal with is turbulent combustion modeling. So the problem is the following. If we look at, this is an image of a DNS, a direct numerical simulation of a turbulent flame. This turbulent flame has two kinds of scales. We have scales that are related to the turbulent flow, as you all know, so integral scales, Kolmogorov scales, and so on. And we have scales linked to the flame itself, the flame thickness and the flame speed. And these scales allow us to describe the flame combustion, the flame turbulence interaction in this regime diagram that is shown below, based on both important number that are the Damköhler number and the Karlovitz number that make the ratio of these time and length scales. And depending on the values of these two numbers, we can observe a large variety of combustion regimes, from very thin flame net regime for high Damköhler numbers to more homogeneous burning to the limit of well-sealed reactor, if for very low Damköhler number, which means slow chemistry with very fast turbulent mixing. So we need to take that into account to see first in which regime we are. So in our application, at least in the one that I have just cited, we are usually at high Damköhler numbers. Combustion is quite fast usually. So we are in a wrinkled thin flame regime most of the time. And all what I will show today in terms of modeling is inside this hold for this kind of regime. So for this kind of regime, we know that there is a strong interaction between the flame and the flow. And we know that the turbulence has several impacts on the flame. It has positive and negative impacts. The positive impact is a wrinkling. So thanks to wrinkling and mixing, the flame speed, the turbulent flame speed, so-called turbulent flame speed, increases a lot, which has a strong, very strong impact on the combustor efficiency. Then we have other impacts like stretching through strain and curvature that may be positive or negative, depending on other properties of the flame. And if you strain too much or curve too much a flame front, you can go to quenching. Quenching is something that you don't want, and this is a negative impact of turbulence on the flame. But for our own purpose here, the main impact we want to model is this wrinkling impact, because this is very important to predict the correct efficiency of a burner. So going back to the basics of turbulent modeling, I will not spend too much time on that because it's something that is now well established and known by the community. If we plot the energy spectrum of a turbulent flow, we know that we have a wide range of scales, which can be either fully resolved or fully modeled. If you are in the advanced model approach, you model all the scales. If you are in a direct numerical simulation approach, you describe all the scales. And if you are in the large eddy simulation approach, you apply a filter at the cutting scale, denoted here as Kc, that is ideally in the inertial range, and that separates the scale that you explicitly compute and the scale, the so-called sub-grid scale that you will model. It has been now quite well agreed in the community that for research purposes, the large eddy simulation approach makes a very, very good compromise between cost and accuracy. It allows you to simulate realistic flows and flames with sufficient accuracy in a reasonable computing time. And for all these reasons, it's now widely used in the community. And for what I will show today, everything will be in this context, in this framework of large eddy simulation. Now, we have another, still with the large eddy simulation approach, we still have a problem of the flame description, because usually the flame scale is smaller than the filter scale of the large eddy simulation approach. So we need to do, even in the large eddy simulation approach, we need to do something in terms of modeling for the flames. So you may find in the literature a very wide range of modeling approaches. I will not review all that today. It's not my purpose today, but I want just to show you one approach that we have successfully applied to many different systems or surfax, and this is the thickened flame approach. In this approach, you take advantage of the fact of some properties of the flame where the thickness is proportional to the ratio of diffusivity to reaction rates, while the flame speed is proportional, or to the square root, square root of the diffusivity and same reaction rate parameter. So if you realize that, and if you apply a thickening factor, so-called thickening factor F here, you see that you can increase the flame thickness by a factor F while keeping the flame speed constant. This is very interesting because this preserves the main property of the flame that is useful for design, which is the flame speed. Okay, the flame speed is what controls the flame length and the burner efficiency. So this is something really that we want to preserve, but the flame thickness is not something that we need to preserve, and something that we can increase to make it resolvable on the LES grid. So with this trick, if I might say, we are able to preserve again the consumption rate of the flames, keeping the correct flame shape and response, while making it resolvable on the LES grid. So this is a very nice feature of this premixed flames that we used. And it allows us to resolve the flame front on the LS grid, even for flames that have very small thickness. this is typically what it gives you. If you apply that in a laminar flame case, you see here the temperature profile for the in black for the real flame, and in red for the thickened flame. So you can see that the temperature profile is well smoothed down. So you have much increased the thickness. So this is much less constraining in terms of resolution compared to the black curve. And if you look at the heat release rate, you have moved to a very steep and very narrow peak to a profile that is much, again, much smoother. But what is important to note here is that these two curves, the red and the black, have the same integral, which means that you have the same flame speed. This is exactly what is looked at, and this is what can be this is what makes this thickened flame approach efficient for LES. Now, you have not completely solved the problem, because in the previous slide, I talked about the turbulent flame interaction, which is illustrated here. We see how much the turbulent flow wrinkles the flame front and then increases the combustion efficiency through this turbulent flame speed that derives from this wrinkling. If you look at the thickened flame, like here, this is an example for a thickening factor of 5, you see that the flame front is much smooth. Down, of course, you have increased the diffusivity, so this is expected. But from going from F equal 1 to F equal 5, it's quite easy to see that you have lost a lot of wrinkling, and so-called subgrid-scale wrinkling. So again, we need to do something about that. And this is where comes the efficiency function. This is other ingredient of the thickening flame approach, where you model the subgrid-scale wrinkling, the part that you are missing because of the filter and because of the thickening process. You determine an efficiency function that is simply the ratio of the two thickened and unthickened flame fronts, that you model with a function that is dependent of laminar flame characteristics and turbulent flow characteristics. I will not go into the details on how you determine this function and how it looks like, but what is important to remember here is that you apply this efficiency function to, again, the same quantities, diffusivity and reaction rate. So note here that you apply them differently. The diffusivity is multiplied by efficiency, but the reaction rate now is also multiplied by the efficiency, because of course the reaction rate, the turbulent reaction rate increases because you want to increase the flame speed from laminar to turbulent value. And this is what E does here. So now you have a complete model that is able to resolve a turbulent flame on your LES grid to recover the correct turbulent flame speed. But then you have to know to make sure that your simulation is correct also outside the reaction zone. If you apply this F and E everywhere in your computational domain, you know that in non-reacting zones, if there is mixing, then if you apply this diffusivity correction here, you will diffuse too much. So it's very important to apply these two factors only in the reaction zone. So this is where the dynamic thickened flame model arrives. You apply this F factor only, and also the E factor only in the reaction zone. This reaction zone is identified with a sensor S, which is able to exactly identify where you have the flame front, and then you apply this thickening only at the flame front location. The final equation that you get in your CFD solver is the one here. For example, for a mass fraction, you see that you have so the E and F factors and the sensor here. Okay, the E and F factor here. So don't need the sensor for the reaction rate because it naturally goes to 0 outside the reaction zone. And you see that you apply the E and F only where the sensor is equal to 1. And if you if the sensor is equal to 0, then you can easily find that you end up with, you recover the standard LES equation for transport of scalars with turbulent, in a turbulent flow with turbulent diffusivity here. Now, how can we obtain this sensor? This is a very tricky part of the model that is not so much talked about, discussed in the literature. So I take the opportunity today to discuss that a bit. It is not so easy to find a universal, let's say, definition of the sensor, because if you think again about the complexity of the flames that we can have in drill systems with complex fuels, complex chemistry, possible liquid fuels with droplets, so varying equivalence ratio and so on. Determining exactly where the flame front is located is not so easy. So we have recently developed a technique, an algorithm that is able to automatically detect the flame front in any kind of simulation, and also determine the correct thickening that has to be applied. So how is that done? It based on two ingredients, let's say. The first step is to identify the location of the flame front. This is quite easy to do if you realize that the flame can be identified with some kind of shape of the profile of some quantities. Typically, this could be the heat release rate or fuel consumption rate also. So this particular shape of this source term here is clearly a marker of a presence of a flame. And what you want to detect is the maximum of this function to locate the location, to locate the position of your flame front. And to do that, if you accept this assumption that the flame front is located at this maximum of this function, it is quite then easy to identify it by simply calculating the Hessian matrix of the function that you have chosen, so the matrix of the second derivatives, and realizing that the eigenvalues of this matrix gives you the concavity and the directions of concavity of your function, therefore gives you an indication of whether you are on a peak or not. So by simply, again, calculating this Hessian and taking the eigenvalues, you can identify where your flame front is located. I showed here an illustration on this round-shaped flame on a instructor mesh. This is what it gives you. It quite easily detects this peak of the flame front. Then the second step of the automatic, let's say, thickened flame model is to determine the thickening factor. So for that, again, we want to rely on the simulation itself rather than rely on a priori values of the flame thickness, because again, if you think of spray flames or non-homogeneous equivalence ratio or other complexities in your configuration, there is no such thing easy to define as one flame thickness. So we thought that it is it will be more accurate to rely on the flame thickness evaluation that you have in your simulation. So once you have detected your flame front, you can look at the transverse profiles of this flame front. This gives you this kind of shape. Like, again, this is a F function, so it can be a heat release rate or any other source term that you choose to determine to mark your flame front. From that, you can calculate a thickness. So this is there are several ways, mathematical ways to do it. Here you just take the second order curve here, approximation here. And then you have an evaluation of the flame. That is the flame that is resolved on your grid. Okay, this is not the real flame, laminar flame thickness, it is the thickness of the flame that is resolved on your grid. What you want to know in the second flame, what you want to ensure in the second flame approach is to have the sufficient number of grid points in your flame front in this thickness to make sure that you sufficiently resolve this flame thickness. So for that, you define a number, we call it RC, which is the thickness of the flame divided by the grid size, the grid step size. So typically the user may say, okay, I want 5, 6, 10 points or 20 points in my flame thickness. And then this is how then you will define your thickening factor. Yeah. Okay, this is then what you will do. The user will ask as a target a number of points in the flame front, and then you can apply a control loop applying a given value of the thickening factor and comparing that with the targets that you have, and adapt the thickening factors until the evaluation of the resolution of the flame thickness reaches the target. So with that, it just means that this algorithm will iterate until you reach the user target set, until you reach a point where you have a sufficient number of points inside the flame front. And this is automatically done. So this means that if you have if you have a flame front that has that goes through a spray or through a stratified mixture, then where the flame thickness, true flame thickness may change, then the algorithm will automatically adapt to this change. There is no such thing that an a priori value to which you will try to stick to define your thickening. So this turned to be quite efficient. I will show you an illustration right now. So we first apply this algorithm to the Volvo case. So maybe some of you know it. It's just a flame stabilized behind an obstacle, like illustrated here. It's a configuration that has been computed by many groups. It's quite well known. And this is what you get. This is the front detection. You see that the algorithm, so this is a result of the eigenvalues of the Hessian matrix. And you see that you have the points here that are identified by this algorithm, this Hessian matrix, and it follows quite well the reaction rate. And this is the thickening that has been obtained automatically. So the user only asked for 5 points or 6 points, I don't remember exactly, but this is the order of magnitude to be inside the flame front. And then the algorithm automatically found the right value of the F factor to satisfy this resolution constraint. So this is something that is quite recent, but it's really improved a lot our results, especially in the case of spray flames, because as you will see in a minute, spray flames have very different behaviors compared to gaseous flames, and there is no such thing that one thickness or one flame speed for a spray flame, or there is, but it is not easy to know a priori. So it is very important to have an algorithm that is able to identify, to know this value by itself without any input by the user. This is another, I told you at the beginning that we validate our models on a series of test cases. So this one here, just the Volvo case I just showed before, is a very simple case. This is a more realistic case. This is the SGT 100 case that has been used also by many groups for validation, but it has more complexity, and in particular as well flow as found in analytical engines. And it is something important to see, to check that the algorithms work well on this kind of configuration. So you can see here the sensor and following well the heat release rate. So this is something that has been well established right now. Yeah, just again another illustration of the validity of the whole concept, where you can see here velocity, but also temperature, excellent agreement between measurement and simulation. So we are now able to reach a quite high level of accuracy on this kind of boundaries. Now I come to the very big challenge of chemistry. As I told at the beginning, we are not now only satisfied by only have the correct flame speed of a flame. We want the detailed, at least some chemical description that gives us access to the pollutants, because this, as I mentioned at the beginning, this is a major provocation now. The problem is that if you think of chemistry, the first thing you find is that you have very complex systems with the number of reactions and number of species increasing very strongly, very drastically with the complexity of the fuels. And this is not the main, well, this is one issue, but there is another issue, not in addition to that, is that this species and these reactions introduce time scales, as illustrated here in the bottom of the slide, that are in a range that is much wider than the time scales of the flow. So the slow time scales may be an issue, but they're an issue for modeling, but maybe not for numerical robustness and stability. But we have also a lot of scales that are much slower, much smaller than the flow time scales, which mean that if you are in an explicit integration scheme, you need to reduce your time step drastically to resolve these scales. So this is a true difficulty. Then you also have to couple this detailed chemistry with your flow and your conditions, taking into account possible heat losses, possible dilution, possible, again, spray flame effects that may make the flame front deviate significantly from a laminar flame structure. So it is not clear that using a flamelet concept can be always possible in all these complex situations. So for this reason, we choose to keep the secant flame model approach for these complex flames, because this is one advantage of the secant flame approach, which is that you can keep a detailed description of the chemistry. It does not go through a reduced global, it does not have any assumption linked on the chemistry. So you can use any kind of chemistry coupled to the secant flame approach. So that was, so we take advantage of that. So we keep the secant flame approach for this, to go to complex chemistry. And then we have still to do something about this chemistry for both reducing the number of variables, because we cannot compute all species, and also reducing the stiffness. And for that, we have applied this reduction approach, which is called analytically reduced chemistry, which has been developed for a long time, I think, by people from the chemistry, and which allows to obtain reduced schemes that are still quite accurate, and in which you reduce the stiffness. So I will just give a short description of that now. You can find the details on this website here, where we provide schemes, reduced schemes to the community. You can find download schemes there. The idea is to derive reduced schemes from a detailed mechanism. So of course, we take the detailed mechanism for granted. We are not chemists, as a fact, so we're not able to develop detailed schemes, detailed kinetic schemes. We take detailed kinetic schemes from the literature, but then we apply reduction schemes. It's quite standard the way we do it. You just apply the so-called direct DRGEP, a graph approach, to go from the detailed mechanism to the skeletal mechanism. And then we apply this quasi-steady state assumption, which eliminates the very stiff species So it has both advantage. It eliminates species, it reduces the size of the system, and it also reduces the stiffness. And this is exactly what we want for our simulations. So the good news is that you can do that automatically. Again, as I said, we're not chemists or surfax, so we do not know so much about chemistry, but it seems that these algorithms that we took again from the literature are very autonomous in a way. They do the good job by themselves. So they're able to automatically determine, apply the DRG-AP mechanism, determine the least important reaction and species, and then also determine the quiescent species. So we have implemented that in a code that we call Arcane, that makes this reduction automatically. It is linked to Cantera for the associated flame calculations. And then the user just has to give a detailed chemical schemes and give some targets like flame speed or some species or temperature profiles, and also gives his own tolerance on this target. And then the code does the whole job. And provides you a reduced schemes automatically. What was very interesting for us to observe is that if you look at the error when you reduce the number of species, you can see in this graph down here that the error stays quite constant, close to zero, while you decrease the number of species, and suddenly at some point the error drastically increases. So determining the limit is quite clear. Okay, there is no much such uncertainty on this, and this is why I think this is my understanding why the automatic procedure works so well. It's because it's quite clear when you have dropped a species that is too important. Mathematically, it is quite clear to determine. So that's why the algorithm has no difficulty to make it. We have applied this approach to complex fluids. This is a work that has been done in the framework of a European project JetScreen to see fuel effects. So I chose here illustrations on some projects that are, again, of course, linked to emissions, because this is the main topic of my talk of today. So I said in the beginning that changing the fuel is one possibility considered by industry to lower the emissions. So in this project, there were 3 different fuels that have been tested. I'm not a chemist, so I cannot comment too much about the differences in these compositions, but we just took it. And we could characterize these fuels. You have here an illustration of the different behaviors of these 3 fuels. Of course, the first one is a reference fuel, Jet A1, a reference fuel that is used now. And you can see that they have different behaviors. These results on ignition delay have been obtained with a detailed chemical scheme that comes from University of Milano. Then we applied our Arcane code reduction algorithm to that, and this is what we obtained. So we quite easily obtained, even for these 3 component surrogate fuels, which was quite not too difficult to obtain reduced schemes. So you see, we went from 300 species to only 36. So with, of course, quasi-steady state species, and of course a reduced number of reactions for Jet A, and with a good prediction of ignition delay and flame speed, but also for the B1, where we end up about the same order of magnitude of species, about 31, with also a good agreement between the detailed and the reduced schemes in terms of ignition delay and flame speed. And finally, for the C1. The C1 is a bit more complex. You see that we have more difficulties to stick with the ignition delay for low temperature. So C1, in our experience, was a bit more difficult to handle, but still we had something satisfactory. And then we could apply these reduced schemes in a configuration that comes from DLR. You have an illustration here. It's kind of standard swirl flow. Swirl flame, and just what I wanted to show here today was this plot here, where you have the temperature at different heights for different fuels, sorry, for the A1 and the B1. And you see that we can recover if you compare with experiments. Experiment is here in the blue circles and empty circles, blue circles and red square, to be compared with the full filled blue circle and red square. And you can see that we're not exactly on the curves because there are other uncertainties, in particular linked to the liquid injection, but you can see that we could recover some trend of the fuel effect with an increase of the temperature, with the fuel. So this is very encouraging, and these are very small effects. If you can see, even in the experiment, they are very tiny effects, but we were quite happy to see that our chemistry was able to recover this trend. Now I will go to, I think I have to speed up a bit to two-phase combustion. So two-phase combustion is very complex because it involves a whole bunch of new physics like atomization, injection, evaporation, interaction with wall, and of course turbulent dispersion. So again, we still want to apply our second flame model here, but we now add a Lagrangian approach for the particle, for the droplets. It is important to really take, there are important effects, I mean, in only turbulent spray interactions that can be, that are illustrated here with this animation and droplets transported in a homogeneous isotropic turbulent flow, where you can see that there is a tendency of the droplets to concentrate in low vorticity regions. So this is, of course, very important to capture in a turbulent flame computation, because this means that the fuel will be concentrated in some particular zones of the turbulent flow. Another nice illustration of the complexity of turbulent flame is given here, where you can see a spray interacting with a flame front, and you can see how some droplets, some evaporate before the flame front, ahead of the flame front to feed this flame front, but some are able to cross the flame front, and some also burn as individual droplets in the burn gas zone. So this is a very complex flame structure that has to be represented. To go back to modeling, one important thing is the question of what is the laminar flame speed of spray flame. Unfortunately, this concept still holds for spray flames. You still have flame speed you can measure a flame speed for any kind of spray flame. But what is interesting is that you can see that in the rich zone, you may have a flame speed that are higher compared to gaseous flames flame speeds, which is something that is maybe not so intuitive, because you would say that evaporation introduces a delay. So you would expect lower flame speed. And this is exactly what the Balave-Lefebvre correlation that's much used says. Okay, this correlation just introduce the evaporation in the picture, and then gives you always a lower flame speed. So this correlation is good for the lean zone, but not for the rich zone. So what happens in the rich case? In fact, we have made some simulation of one-dimensional spray flames, or two-phase flames, let's say. And what is interesting to see is that if you plot different quantities, so here the heat, the fuel consumption rate, but more importantly the fuel evaporation here, if you compare with the flame itself, that is indicated here with this oxygen and fuel mass fraction, you can see that in fact there is incomplete evaporation in the flame zone. Okay, this can happen in very rich cases, or depending also on the diameter of the droplets. The evaporation is not complete, which means that the equivalence, the fuel amount that the flame burns is not the fuel amount that you feed the flame with. And if you are overall rich, and if you go back to the flame speed curve with equivalence ratios, you see that you move from a very rich point, this your nominal equivalence ratio, but what the flame sees is a lower equivalence ratio because again, the fuel has not fully evaporated before the flame front. Therefore, the flame speed increases because you come closer to stoichiometry. And this is exactly what happens. And this is what explains the higher flame speed in some situation in overall rich spray flames. Then we went, when we realized that, so we proposed a new correlation for the flame speed of this spray flame. So we introduced an effective equivalence ratio, taking into account the fact that you may not evaporate the whole liquid before the flame front. And if you look here at the comparison of flame speed obtained, measured from simulation and taken from the correlation, you see that we have a good match in the lean case, which is also not so bad for the Balab and Lefebvre correlation. As I mentioned, for lean cases, this works well. But for rich cases, you can see that the correlation really is able to describe this increased flame speed for rich cases when evaporation is not so fast. You can also see another feature that we have studied here, which is the impact of the slip velocity between the droplet and the gas, because this also impacts a lot, of course, the amount of evaporation inside the flame front. It has, as you can see here, a lot of impact on the flame speed. But I will not go into details into that now. The main message here is that the flame speed of a spray flame is not something that is easy to determine a priori, and for some modeling approaches, it can be a difficulty. We extended this correlation to multi-component fuels, typically those that I showed previously. So you just take into account that you have several evaporation characteristics times, and you can see that again, you have also for rich cases this increase of flame speed, and the correlation is able to capture it. Now, how should we apply our thickened flame approach model to spray flames? The issue is the following. We have in a spray flame, we have evaporation reaction, okay, and the balance between these two gives you the final flame structure. Now, if you apply thickening to the gaseous part of the flame, let's say, then the reaction zone changes, like is modified as shown here, and of course you see that the balance or the relation between evaporation and reaction changes a lot. So this means that you have to do something about evaporation also. And this is illustrated here. We have made, again, a series of simulations with looking at the flame speed depending on the equivalence ratio for given different droplet diameters. And if I take this point, for example, we have observed that, of course, if you do not include the F factor if you do not apply the F factor to evaporation and drag, then you are not able to recover the correct flame speed. So this means that when you do spray flames, you also need to apply the thickening to the exchange terms between the two phases. So this is also an important note for this modeling system. So with that, we are able to compute spray flames like this one shown here, which is a test case from a configuration from Korea that has become a test case. Many groups have computed it, and with this approach, we're able to obtain the correct flame structure and flame liftoff. Typically, we are able to really go into much details in the flame structure, and in particular the way the spray flame is stabilized with various zones, with describing the very complex spray flame structure, where you have zones where, for example, in the zone A here, you have air with small droplets that behave very differently from the zone, for example, B2, which is an external reaction zone with a lot of pre-evaporation and so on. And you see this really specific flame structure that we have here is really well recovered by the LES with the model that I have just presented. So with all this, we can predict emissions. So just an illustration on one configuration, which is another LDA configuration, which you can find in these papers. Again, it's a swirled flame with kerosene, and on which there was some nice measurement of emissions, CO, CO2, and NO. So we applied our thickened flame approach with Lagrangian solver for the droplets and chemistry, analytically reduced chemistry. Okay, this is just to show how it looks like. This is quite standard. This is swirled spray flame. This is to show some validation, so in terms of temperature and products. But you can see here already the CO profiles at various rates above the burner, and you can see the good prediction of the CO. It was interesting also to go into more details in this CO field. In particular, we could see that this particular shape of the CO with some peaks here around the sides was really linked to some particular chemical processes that occur close to the cold walls. This is something that was very interesting to observe, and that only our thickened flame approach with like explicit chemistry, let's say, is that naturally captures without any further modeling. For NO, again, we had also a nice comparison, and so we were quite happy with these results. So demonstrating that we're able, with the model that I have presented, we're able to predict these pollutants. I will go now quickly. I'm maybe have 5 more minutes to go very quickly through soot. I will go very fast here because I'm running out of time. So just to mention that, okay, soot chemistry, we all know that it is very complex. It's only, there is a gaseous part here for incaption of soot particles, and then there is a lot of heterogeneous chemistry and particle-particle interactions that play a great role in soot evolution. We also now know that we need to describe the soot particle population because we have a high number of particles and can be a kind of difficult challenge. And we also have a strong polydispersity. So this population are usually classically represented, described with a number density function. And of course, soot measurements are a key point in our approach. The only thing I want to show today is the fact that it is possible to compute soot, to predict soot with the Lagrangian tracking approach. You can find in the literature a lot of works on sectional method or method of moments to describe this soot population. The idea behind being that describing the trajectories of all soot particles would be too costly. In fact, we have developed some algorithm and a methodology that makes Lagrangian tracking in fact more computationally efficient than this sectional method or method of moments, if it is to correctly capture the probability, the size, the soot particle size distribution. So we took, I will not detail too much the chemistry because we only took something from the literature, and so we mostly developed this Lagrangian approach. I want to also mention the Soprano project, European project, in which new data sets could be produced that could be interesting for the community to better characterize soot oxidation and the complexity of soot evolution in terms of evolution, and also the sensitivity to the fuel nature. I just want to go to say a word about the Lagrangian tracking. There are two main points here that you have to consider if you want to do that. The first one is is about collision. You cannot, of course, describe all individual collision or between a pair of particles, because it would be too costly. So for this part, of course, we use the stochastic algorithm. This is quite standard. I will not detail that here, but it's a stochastic algorithm for collisions that you can find in any kind of code for simulating droplet particle populations. And the other important feature is to control the statistical convergence of your population. You have to make sure that you compute that in each cell of your simulation you have enough particles to be statistically converged and get correct results without increasing too much your computational costs. This means that you have to apply sort of merging and splitting procedures to control the number of particles per cell that you want to keep in your whole simulation. So with this algorithm, we were able to construct a whole methodology with the Lagrangian approach. And we first applied that to this configuration from DLR. This is so-called the ISF4 for people who work on soot, probably know it. And what we did here, just compared two various approaches for the particle simulation description. So we do the monodispersed Eulerian, like method of moment approach. We compare that to the monodispersed Lagrangian and also polydispersed Lagrangian. But if you compare the two monodispersed case, which are the line here and the crosses, you can see that they give very close results. Okay, which means that we have ensured that, and this is expected, but the Lagrangian simulation gives the same result as any other Eulerian approach. So with that, we were able to apply to make some prediction of the soot in the burner from UTS, which uses also Jet A1 as a fuel. And so we made the simulation. So note that in that case, we have two kinds of populations. We have droplets for the fuels and the soot. So you have to distinguish between these two. And we also had to adapt the chemical description because we had the complex fuel, which is Jet A1. So I will just keep that, just showing that, okay, with that approach, we were able to, of course, obtain a nice and detailed description of the flame itself with various combustion regime, either diffusion close to the injector or premixed more downstream. But also we were able to obtain a quite detailed description of the soot population and evolution. We were able to identify the zones of nucleation, growth and oxidation, and also the shape. I don't describe that today, but with the way also to, we also included a description of the shape of the soot. If I go back, I cannot, yeah, maybe here. You can see here that the prediction of the soot volume fraction was quite satisfactory in that case. You have here the lines are the prediction, the simulation, and the symbols are the measurements. And you can see that we were able to obtain the correct location levels of soot. So these are very encouraging results. And just in terms of computational cost, in fact, we could observe that the Lagrangian approach, if you do it the way we do it with the correct and efficient handling of the numerical particles, let's say, the overcost of the Lagrangian is very small, much smaller if you compare to any method of moments, for example, if you want to capture the correct particle size distribution. So this was quite satisfactory also. So now it brings me to the conclusions. So I hope I'm still in the in the time. So just to conclude, to the fact that, so we can say that we have a methodology based on large eddy simulation, including semi-detailed chemistry, Lagrangian approach for the liquid fuel and soot, that is able to describe turbulent, gaseous, and spray flames to predict pollutant emissions, and also transient behaviors that I will show an illustration just after, in complex geometries. Now from that, it is possible to, of course, couple these simulations to other physical effects like thermal radiation, conduction, or electric fields, or whatever. So this is something that will come probably in the future. Of course, we still have to work on some aspects. Typically, soot chemistry is something that is is far to be sufficiently known now, but we have the tool to include more accurate or more detailed soot chemistry in the solver. Multi-component liquid fuels still remains to be studied. We are just at the start of it, as well as the reduced chemistry for fuel blends. And we also need to continue the work on turbulent combustion modeling, because you may have noticed that when I spoke about the second flame approach, I spoke mainly about premixed flames. But we know that with the change of fuels, typically if we switch to hydrogen, we may see more non-premixed flames, which also happen more in spray flames in 3D complex geometries. Just to give you to finish with a nice movie, I just wanted to show what LES allows for transient cases. This is an ignition of a spray flame in an annular burner, a lab scale annular burner. So this gives an idea of what can be done. You can the simulation nicely reproduces the flame propagation to the hood burner. So this is very important and very interesting for application. And it does not give only a nice movie, it also gives a quantitative good results if we compare with the experiment. The images here compare the simulation and the experiment at the same time. And you can see here in this plot the time of ignition of all the different burners, and you can see that we have a very good match. So these tools are this LES approach with all the models that I mentioned are very powerful and open the way for many, many studies of different situations. And this ends my talk for today. So special thanks to all the students who have worked on the various aspects that I have just mentioned. And if you want to know more details about all I have presented today, you can go to our website here, and the publication and PhD thesis are all there. And so you will be able to find a lot of details there. And I think I will stop my talk right now. And thank you for listening, for those who are still there. And of course, I'm open to questions and discussions.
Okay, thank you, Bénédicte, for your very interesting talk. It was really, really interesting, covering a lot of aspects from modeling to chemistry and then applications. We have already received some questions, so I will ask them to you. So the first question that we have received is from Dr. Ahmed Elban. He is more interested in understanding more the LES modeling for flames. I think that you covered this aspect, especially in the first part of your talk. I think that you can, probably spend a couple of words on how the subgrid modeling is affecting your flame structure predictions.
So what is exactly the question? It's about the subgrid scale modeling?
Yes, I think LES modeling approach for flames.
Okay. So you want me to show maybe?
Yes, if you want to go back to the slide, I think
the slides. Okay. Mm-hmm. Yeah. This is really linked to the properties of premixed flames. Premixed flames have a given thickness and given flame speed, and these properties are linked to the diffusion on one side, and the A is characteristic time, an inverse characteristic time scale of reaction of combustion chemistry. So you can show theoretically that thickness is proportional to the square root of D over A, while the flame speed is proportional to the square root of D multiplied by A. So the problem we have, the first problem we have with premixed flame in LES is that the flame thickness is smaller than the grid step, the grid resolution. If you do not do nothing and you make an LES without using only the feature, the standard, the normal transport properties and chemical properties of the flame, then the simulation will crash because you just don't resolve the flame thickness. So to avoid that, we apply a thickening factor, F, as it is shown here. So we multiply the diffusivity by D, which increases the flame thickness, but then we also divide the reaction rate by F to preserve the flame speed. With that, we are able now to resolve the flame on the grid, on the LS grid, because it has been thickened, without changing the flame consumption speed, which is the main important thing if you think of burner design, because when you want to know where your flame will be and how long it will be, this is the quantity that will pilot this flame length. So it is very important to preserve this quantity. And so this is something that we found very useful, because with that, if you make this transformation, then you can do your LES, you can do your computation of the flame on your LES grid, and it will be stable numerically, it will be resolved. Then, of course, when you do that, you have not correctly modeled the subgrid scale effects that I mentioned just after here. The fact that you have some interaction, smaller scale interaction, subgrid scale interaction between the flame front and the turbulence. And this is where comes this efficiency function that allows to recover what happens at the grid scale, and you just apply that again to these two quantities, D and A. So you can show that this efficiency acts again as an increase of diffusivity, like turbulent mixing, and also it increases the reaction rate because the wrinkling increases the flame speed. I mean, the turbulent flame speed is increased compared to the flame speed through wrinkling. This is exactly the role of this efficiency function here. So okay. Yeah, is that clear enough?
Yes, I think that is enough. And I mean, if you want to know more about this, I think that we can refer to our website where you can find publication where all these models have been presented. The next question are from Professor Jay Gore. So the first question is still on the thickening flame model, actually in its application for spray flames. Mm-hmm. The problem in spray flames is that you have multiple equivalence ratio. So you have a partially premixed combustion. How do you handle that in the thickening flame model? Linked to this question, there is also another question from Professor Gore. Do you observe double flame structure in spray flames? And if the thickening flame model is able to correctly capture these complex flame structures?
So, in fact, the thickened flame model has no difficulty in describing spray flames because combustion always occurs in the gaseous, in the gas phase. Okay, so imagine you have droplets, they evaporate, then you have a heterogeneous equivalence ratio. No problem. The thickened flame, the flame will see it. You don't need to do specific treatment for that. Okay, provided you have correctly determined the thickening factor, as I just showed in my presentation just after these slides. So there is
no. Does it capture the rich flame and the lean flame that you described, a double flame structure? You mentioned that there were two different flame speeds.
Yes.
And sometimes, in fact, the flame speed was faster than the overall equivalence ratio. the speed corresponding to the overall equivalence ratio. So is that complexity captured by the thickened flame model, that sometimes there can be two different flame speeds, one faster than the equivalence ratio of the mixture?
Yes, exactly. This is the advantage of the thickened flame approach, because you do not assume you don't pre-assume the flame structure. So the thickened flame approach, again, you just have thickened the flame front, but then you keep the reaction source term. So if the reaction source term sees a rich flame, locally a rich zone, it will burn as a rich zone, and in the neighboring cell, it sees a lean zone, and it will burn a lean zone. So yes, it effectively captures this very interesting effect of spray on the flame speed. Yes, it does.
Thank you. Thank you. That's important to capture that complex effect. Yes.
Yes.
This was related to the soot, and I noticed that the measurements of the soot in one of the very late slides showed parts per billion level soot volume fraction. And then in the computation slide, it showed parts per million. So I just wanted to understand if the resolution for measurements as well as computations is at the parts per billion level or at the parts per million level.
In that case, it is part per billion. Yeah, so it's.
And the computation and the precision of the measurements is in the parts per billion range now for this particular case?
Yes.
That's wonderful, because earlier slides showed parts per million, and that was for an ethylene. That was ethylene.
Yeah, maybe I have to check again if there is no mistake. Frankly, from now I cannot say more about that.
So this is an important thing, because a factor of 1,000 is if the precision has improved by a factor of 1,000, or if the emissions have decreased by factor of 1,000, both are very good advances. Thank you.
Thank you. So the next question is from Dr. Zhanglong Zhu, and he was interested in your pressure swirl configuration, so in your spray flame configuration. How do you fix the droplet size and droplet size distribution and velocity? So how do you? Yeah, injection.
Yes, okay. I didn't talk at all about injection and atomization. And this is a very interesting question, of course. This is, I would say, one of the main weaknesses of our simulations right now, frankly speaking, because we do not have at the moment any model for atomization. We are working on that, but at the moment it's not yet in place. And what we do for the moment, we just put in the simulations the knowledge of the spray we have from experiments. So typically we take the droplet size distribution and velocity that we have from experiments, from measurement. If we don't have these measurements, then we take some standard, let's say, shapes of the droplet size distribution and velocity based on very simple concepts and correlations. But again, so for stabilized flames, this seems to be sufficient. Usually, I mean, the sprays are not so different from one case to the other, and also you can see, you can observe that the spray, they do not last very long. They are very fast evaporated and burned, so it's not so much sensitive. Now, if you speak about ignition or instabilities or any other transient situations, then this comes a difficulty. And this has motivated studies at Surfax to develop atomization models that are suitable for 3D LES of industrial system, which means it is not a level set approach or a resolve interface approach. because this is too costly for 3D LES. It is more based on diffuse interface methodologies. But it is ongoing work, and I hope to soon give you new results on that.
Okay, thank you, Bénédicte. Next question is from Professor Wang Fei. Actually, he asked two questions. The first one is on the computational cost of LES coupled with the stochastic algorithm in soot prediction. This cost is very high. So in your opinion, it is possible to lower the cost?
This cost is not high. In fact, this is what we have shown. In the literature, you often read that computing Lagrangian soot particles is too costly. But in fact, if you have a correct data structure, if you control statistical convergence with the good control of the number of particles that you have in your simulation, then the overcost is what I said is like 17%. So convert additional, I would say. So compared to a sectional method or method of moments, including, aiming at predicting polydispersity or spread PSD, it's much less costly. It's much less costly, in fact. So it's a message that I want to give today, that I try to promote, is that Lagrangian tracking of soot particle is not costly if you make it properly. If you take good advantage of your parallel algorithms, and again, it's all linked to the data structure and the way you handle the particles. It can be very, very small overcost. And this is what we have observed. The reason why we choose to go to Lagrangian soot tracking is based from our experience on droplets, on spray flames. Because we observed that it was the case for spray flames. The cost of computing the droplets was completely negligible. So we thought that maybe it would be the same for soot, and it occurred to be the case. It happened to be the case.
Okay, thank you very much, Bénédicte. Another question still from Professor Fei. It is possible to model the ignition process of swirling flame with the thickened flame model approach?
Yes, there is a subtlety here. When you do ignition, when you compute ignition, at the very, very beginning, the very, very early instance of ignition, you have to make sure you have to deactivate the thickening, because if you activate the thickening as from the beginning, then the thickening will you are not already in a propagating flame regime, so you just have a kernel, and so if you activate thickening, then the kernel will diffuse too fast, and then you will not ignite. So what we do, at the location of the sparking, we have a small patch of very refined mesh, like almost DNS, if I might say. Where we are sure that the flame kernel will be resolved, but it's a very small patch, so it's not costly. And then we compute the first instant of the kernel of this very resolved zone. And as soon as the kernel has left this patch and has entered into a propagating flame regime, then we remove this patch and we activate the thickening flame approach, and then the flame propagates. So yeah, the very first instance have to be performed in DNS mode.
Okay, thank you, Bénédicte. Another question still on the thickening flame model. For non-premixed flame, it is important to thicken the diffusion layer?
So for non-premixed flames, non-premixed flame behave completely differently as premixed flames. So we are now currently working on that, but I can tell you first hints today. If you make a diffusion flame, as you may know, has no intrinsic thickness as a premixed flame. The thickness of a diffusion flame is piloted by the strain rate of the flow, which means that if you compute a diffusion flame on a coarse grid, it will never crash. The flame thickness will always adapt to the resolved strain rate, so the thickness will be resolved. Okay, so that's the first thing to know, that it will never crash. So that's very important to realize. Then, of course, you have to take it to properly model the subgrid scale effects and so on. But you don't need, when you do a diffusion flame, the mesh, in fact, does the thickening. You don't have to apply artificial thickening as in a premix flame, because the premix flame will always want to tend to its intrinsic thickness, but not a diffusion flame. So it's a completely different story.
Okay, thank you again, Bénédicte. So we change a little bit the subject. We talk now about your chemistry reduction approach. For your chemistry reduction approach, beside the QSS and DRGP, do you also tune reaction parameters like rate of constants, pre-exponential factor, in order to match your target? And
No.
if yes, what kind of method you use?
No, so we do not. This was one motivation for us to go to this type of description. We didn't want to optimize or to tune the reaction constant parameters, because we keep real reaction. We keep true reactions. So we keep true reactions with their uncertainty, of course, but we do not touch the constants. We don't want to. We could do. Okay, we could tune the constant and then probably reduce more. It can be useful in some situations, but usually we don't. Usually we keep, in most cases, or in all what I've shown today, we haven't tuned the constants.
Okay, so I think that we have the time for one last question, and it is from Dr. Suo Yang. He's asking about your Lagrangian particle. So when you talk about your Lagrangian particle in the code, is a statistical sample or a pseudo particle consisting of several physical particles?
Yeah, so we have this concept of numerical particle. Okay, so one particle, there is a possibility to have a spray represented by a set of what we call numerical particle, in which each one numerical particle represents a number of particles having the same statistics. Okay, with that you can decrease the number of particles that you have in your simulation. But again, you cannot decrease too much, because you have to ensure statistical convergence. So what I prefer, I mean, for me, the important parameter is the number of particles in a control volume. Okay, and we know that for this phenomena, we need like 100 or 10 or 1,000 particles to ensure statistical convergence, and then we make sure that we reach this statistical convergence either in space or time. Okay, you may have maybe at each instant only 10 particles, and so if you want 100, then you can wait until you have collected the statistics of 100 particles in time. Okay, so but again, it's a statistical convergence that makes that pilots the number of numerical particles that you want to compute.
Okay, so I think that now time is over. I would like to thank you, Bénédicte, one more time for today's talk. And I just wanted to know all of the attendees that this talk has been recorded. So, I mean, will be available on the YouTube channel of the YouTube channel of the conference pretty soon.
Thank you very much to the audience for listening and for the invitation, of course. And goodbye.